Okay, differentiate this to obtain its derivative. So this one is an antiderivative of a to the x. Antiderivative plus a constant c is the indefinite integral of that one. Okay, when the base is a positive number, this exponent can be arbitrarily real. So this reminds us the power rule. Before, we only can deal with rational power, but here we may consider real power, real power. So the small step R. Before, when R is an irrational number, this one is not defined. Of course, if R is an integer, for example, a positive integer, x can be arbitrary real number. This result is also true. So when this is defined, x is positive and R can be arbitrary real number, then this result is still true. Let's see. What is x to the rth power? By definition, this is, now we have, in terms of exponential function, logarithmic function. Okay. E x, not x, EU. EU times du dx. Okay, here we already used this one. Okay, the first factor is x to the rth power. And for the second factor here, r is a constant relative to x. So differentiate this one with respect to x, we can use this formula. When x is positive. x is x with the exponent 1. Aha. Finally, this is what we have learned for a long, long time. The exponent can be arbitrary real number, okay. Though we already know this long time ago, but we know that this relation just that it is valid only for rational, but for some suitable x. But now we extend to arbitrary real number or arbitrary real number R, because now this one is already defined in terms of natural exponential function and natural logarithmic function. Finally, let's take a look at the graph of general exponential functions. Suppose A is a number greater than 1. The graph of this exponential function looks like this. Again, third one. Why? The reason is this one is defined to be E x ln a. So if ln of a is a positive number, for example, this is 2. If we multiply some positive number here, then the new graph of the new function is quite similar to this one. Since if originally here a, this value is E a. Here we have to use half a to obtain the same height. Same height. So this means the graph of this function is obtained from this one by how to say this? Contract. Yes. Shift this graph more close to y-axis by a rate of a factor 1/2. This is 2, then 1/2. If this is 1/2, then 2. In general, when a is greater than 1, then ln of a, of course, is greater than 1. It is positive. So this one is positive, and the graph of this function is quite similar to the original, the natural exponential function. Okay, next, If A between 0 and 1, okay. In this case, ln of A is negative. It's negative. Okay, ln of A. If A between 0 and 1, then ln of A is negative. Is negative. If this is a negative, means by definition of A to the x power, this is negative. So the graph of this one can be obtained from this one with a reflection about y-axis. Then dilation or contraction. For example, if A here obtain EA, then we have to choose minus A to obtain EA, the same height. So the curve, the graph of this one and this one are quite similar by reflecting. By a reflection about y-axis. If this is not one, then dilation or contraction about y-axis. Okay. So this is the reason why when A is greater than 1, the graph looks like this. When A between 0 and 1 is a decreasing function. Okay, take a break.